Good morning, Astronomy 1010. Welcome to our final week of lecture 13. Woo! The class is coming to an end. This week, we're going to learn about Jupiter and the Jovian moons. We have a lab today on the revolutions of the Jovian moons. I may farm that out as a pre-record. Now, the more I think about it, the more I think about how much I can get done if I do that. Because I was coming back from New York last night, I didn't get in until after midnight, and I was just too zonked from it all to grade papers. So I'm going to try to catch up on that grading today. I will finish the grading by the end of this week or so. Most of you are going to opt not to take the final and to use your midterm grade. I just want to keep reminding the class about that so that if there's anyone out there who does want to take the final for some reason, they can let me know, please, for the love of God, before the last date, okay? So I'm prepared and I know about that. But probably most of you will not do that, and that's fine. And that means after Friday's class, once you submit your lab and homework for this week, I guess that will sort of be it, right? I realized that something I have not done is I want you guys to be able to do a student rating of instruction for me where you evaluate your professor. I definitely need to figure out how to flag those things. For those of you who haven't done this before, somewhere in your My CCRI, is this my CCRI or is this my CCRI? Let's see what happens here. Somewhere in your My CCRI, which I hope I'm logging into, there should be a tab for SRI, Student Ratings of Instruction. Now, for me, it's under Faculty Admin Tools. For you, it might be under Student Tools. I don't know. You'll have to figure that out, but then you can select the term Spring 2021. Oh, oops, there we go. Come on. I'm not sure how I'm supposed to turn these on. I forgot because I've only had to do it once or twice. So I need to call our department administrative assistant, Paula, knowledgeable as she is, and she will tell me how to activate those, okay? So maybe that's something I can do today while you guys are cranking out the moons of Jupiter. All right, so what are we gonna do today? We're gonna say one little thing about Earth's atmosphere that relates to Jovian moons, and then we're gonna talk about the gas giants themselves, and hopefully on Thursday we'll get into their moons, which is a very interesting topic. I want to start off by telling you guys about Hadley cells. And this is something that's been coming up in all kinds of weird places. For instance, this week, I almost sent you guys an article I was reading in either the Washington Post or the New York Times about some experiments being done in the Martian atmosphere. And they several times referenced measuring the deuterium to hydrogen ratios to learn about the atmospheric history of Mars. That's something that we talked about in our class, so I thought it was cool to see it in a popular news article. Unlike Venus, Mars and Earth have significant wind storms, and they are related to climate and weather. And we're also going to see these effects on Jupiter. So since I didn't quite get to pull these in, shall I say, to our last week's lecture, I thought it might be kind of cute to start out here. Hello, Ryan. If you've ever looked at wind patterns on Earth, there's a direction that winds blow which depend upon your latitude. I think they call them the trade winds along the equator, which blow from west towards the east. Along temperate mid-latitudes, the weather that we watch on our weather stations or on our televisions, we always see these storm systems migrating from the west coast to the east coast of the United States. And there's a reason for that direction of wind flow. In the polar regions, once again, the winds blow in an easterly direction. And that has something to do with two things. One is the rotation of Earth. The second is convection in the atmosphere. Now I'm going to pull up my blinds because the wind is making some noise. How symbolic, okay? And meanwhile, you guys can tell me what you think about convection. What is convection? Tell me about convection. It's heat transfer, or I guess heat is a transfer of energy. Okay, it's a heat transfer thing. What do you think, Jenna? That's somewhat correct, Ryan.
I'm thinking of a convection oven, so heat rises
Yep.
and like a bulk transport. So the hot bubbles rise and the cool bubbles sink.
Exactamundo. Now let's imagining that's happening on a planetary atmosphere. We know that the ground is radiating infrared light from below. That was part of our lectures last week. Where are we going to get heat rising on Earth? What's roughly the warmest location on Earth, if we think about the whole planet?
The core.
Well, we're just talking about atmospheric circulation right now. So
Oh,
energy flowing from the core doesn't directly relate to the atmosphere. The atmosphere,
the equator.
that's right, the equator. And the first person who ever described this was a scientist named, I don't know if it was James Hadley, but I can't remember now, something Hadley. And these so-called Hadley cells are named for his scientific description. Warm air being heated from below rises over the equator. The warm air displaces cooler air near the poles of Earth, and winds blow the cold air along the surface back towards the equator. And this giant cell is, of course, just good old-fashioned convection, one of our three modes of heat transport. But when it happens in a planetary atmosphere, we call these cells a Hadley cell. Let's take some quick notes on this. So let's title this Atmospheric Circulation. Our first key concept of the day is the concept of a Hadley cell. And Hadley cells are giant convection cells that occur in a planetary atmosphere. We've talked about them before, but I haven't given you notes on them, so I wanted to fix that. In a planetary atmosphere. Okay, and we could even draw a sort of picture of them, right? Here's Earth, right? Here's the equator. Here's the North Pole. We have sunlight beating in from the right. Then we have the ground heating up, displacing hot air along the equator and cool air along the surface from the poles. On Venus, which has no rotation, there's one Hadley cell per hemisphere. Venus has no rotation, so there's one Hadley cell per hemisphere. As a result, thermal mixing, shall we call it, leaves the planet at one single temperature. So it leaves the entire planet at the same temperature. And that temperature, of course, is around 460 degrees Celsius, which is quite hot. On Earth, however, Hadley cells are broken up by the Coriolis effect. Jenna, let me know when you're done. Or Kim, are you good? All right. I decided I didn't want to squish into the bottom there. Eraser. on Earth and to some degree on Mars, although it turns out that Mars's atmosphere is so thin that it doesn't effectively hold as much heat, so it kind of doesn't matter so much. But on Earth and Mars, the rotation, which is about 24 hours for both, splits convection into a set of triple Hadley cells. And I'd like you to underline that because that's a key concept. Due to the Coriolis force. Let's look at a picture of the triple Hadley cells, and then let's talk about the Coriolis force as well. In fact, let's define it while we're doing the note thing. Unless you've taken a physics course, you've probably never heard of the Coriolis force. However, it is related to another force that you might have heard about, the centrifugal force. The centrifugal force is the force that pins you to the edge of that giant amusement park ride, which spins around really fast and pins you to the wall, and sometimes they even drop the floor out from underneath you to really freak you out. There are forces, fake forces, that show up in rotational coordinate systems. And these forces are not really due to like gravity or friction or some kind of fundamental force. They're due instead to the act of rotating itself, which creates accelerations and things. So the Coriolis force could be described as a twisting force. A twisting force that results from motion within a rotating coordinate system. It's a twisting force that results from moving inside of a rotating coordinate system. That probably sounds like a bunch of gobbledygook to you, so I'm going to give you some examples once you're done taking that down. All right. Bear with me, students. Jenna, Kim, Ryan, can I show you the picture now? Okay. So let's go ahead and let's share our screen. And let's start off here. I got this kind of crappy picture, and I want you guys to imagine that this pink disc represents a record player. So, oh, I bought some records in New York this week. If you're a big nerd like me, and you love records, you might know that records spin at a rate of 33 rotations per minute, at least for one of these good old-fashioned LPs, okay? So you put your record in a record player, and as it spins and rotates, the record is rotating at, they call it 33 RPM. That means 33 rotations per minute. You can think of 33 rotations per minute as something like an angular velocity. Here's something to consider. A record player is what we refer to in physics as a rigid body rotor. A rigid body rotor means all parts of the record need to spin at the same angular rate, no matter where you are along the radius of the record. And that should make sense to you guys. 33 rotations per minute holds for this track as well as this track on the outside, okay? Now, one day there were a lot of ladybugs around, and a bunch of ladybugs landed on my record as it was spinning, and I watched them go flying around the record, and that was kind of funny. I want you guys to imagine that there are 3 ladybugs on my record, one here. Let's call this ladybug A. Let's imagine there was a ladybug over here, somewhere in the middle of the radius of the record. We'll call that ladybug B. And here's a third ladybug at the outside of the record. We'll call her ladybug C, okay? Ladybug A, B, and C are all in a race going around a racetrack, just like runners in a sort of 100-yard dash or whatever. Except normally in one of these races around a racetrack, we all know that the runner on the inside has the advantage over the runner on the outside. Why is that?
Less distance to travel.
Easily said. All right. However, in this case, in a rigid body rotor, all three ladybugs need to win the race at the same time. They need to complete the race in the same time. And what that means is they cannot all be traveling at the same velocity, right? It must be true that ladybug A is traveling kind of slow, ladybug B is traveling kind of medium speed, and it must be true that ladybug C is traveling the fastest in terms of velocity through space. Just think about it in terms of the circumference of a circle. This ladybug travels the entire circumference of this large circle in the same time that ladybug A travels the circumference of the small circle. So now we can see that ladybug C must be the fastest. Now I want you to imagine something. What if ladybug A decided to take a journey and walk from the middle of the record towards the edge of the record? As she started stepping over new parts of the plastic disc, she would be standing in new areas of the disc that were automatically traveling faster than her. In other words, she keeps stepping on ground that's moving at a rate faster than she is. The result is she will feel this awkward, seemingly imaginary, but actually quite real twisting force that deflects her down and to the right as she steps over areas of the record that are moving faster than she used to be. This is the Coriolis Force. Okay, now you guys try it. What if there was kind of a mutant ladybug? Let's say a blue ladybug, or sometimes they're yellow actually. Here's a blue ladybug, and the blue ladybug is gonna move from the edge of the record towards the center of the record. My question to the class is this: will the blue ladybug experience a Coriolis force that twists her up and to the right? Or will the blue ladybug experience a Coriolis force that twists her to the left? What do you think?
Up and to the left?
That was my guess as well.
Unfortunately, that's incorrect. It's to the right.
To the right.
You're a little late, Austin. All right. Why would it be to the right, though? Can anyone explain that?
I guess like moving from the center out, it would go to the left. So inversely, going from the out to the center.
Let's focus on causes and effects. Out here, the ladybug is traveling fastest through space, correct? And this part of the record is traveling slower, at a slower velocity through space, correct? So as the ladybug journeys from a fast part of the record towards the slow part of the record, she will be continuing to keep a bit of her fast momentum, and that will twist her up and to the right. Believe it or not, this actually played a role in a decisive campaign of battles that took place during World War I naval history. For the first time ever, UK boats were battling these German U-boats, which were the precursors to submarines. And they were, for the first time, firing artillery shells over many, many long distances and many lines of latitude. Of course, Earth is also a rigid body rotor. Like a record player, every part of Earth has to complete a spin in 24 hours. And that means that on Earth, your velocity through space along the equator is actually much faster than your velocity through space closer to the North Pole. In fact, when you get to the North Pole itself, you spin on your axis like a rotisserie chicken, but you don't really have a velocity through space because you do not traverse a circumference each day. One of the things that was happening during these battles, these naval battles, is the British boats who were trying to hit the German submarines were firing artillery shells over long distances, and the Coriolis Force was twisting them and causing them to miss their targets. Only after correcting for the Coriolis Force were they able to sink the German U-boats and thus win the war. In fact, clouds and convection cells, which push air from warmer areas of Earth to colder areas of Earth, will experience the same set of Coriolis forces. And this is where a lot of our weather and climate patterns, or weather patterns, come from. One of the first effects is that the Coriolis effect splits circulation on Earth and to some degree on Mars into a set of triple Hadley cells. And as I've mentioned in a previous class, the triple Hadley cells serve as a kind of small refrigeration unit. This convection cell keeps warm air near the equator. This convection cell keeps moderate temperatures along the temperate zones. This convection cell creates a polar region with cold temperatures up there. Have you guys heard of the polar vortex in the wintertime where you have those hard cold snaps? That's where fluctuations or changes in Earth's weather pattern cause super cold air from this cell to, remember how Texas was having those freaky snowstorms this winter? Remember seeing that in the news with people shoveling snow in Texas? That was because this polar cell actually temporarily broke into the temperate zones through turbulence in the wind patterns. So they can obviously have pretty serious weather effects. In fact, as the book points out, something to think about is this boundary right here between they actually have names for each of the Hadley cells. In honor of, I think, James Hadley, or whatever his name was, who created them, we still refer to these cells as Hadley cells. This cell is known as the ferrule cell, and this upper cell is known as the polar cell. And you can see that they create wind patterns which are quite complex. Northeasterly trade winds in the equator, westerlies along temperate zones, and I forget what they call the air currents in the Arctic, but any ancient mariner or sailor would have known about these because you can use them to travel from continent to continent, right? If you get into the jet stream or something. An interesting point that the book makes that I would like to point out is the boundary between the ferrule cell and the Hadley cell occurs right around 30 degrees north latitude. And the constant pulling of air, notice for instance, that you get some slightly different convection patterns. At this interface, can you guys see how air is being pushed down? But look at these two interfaces. Here, air is being pushed up and air is being pushed up. One of the weird effects of air being pushed down is these convection cells drag moisture off of the surface of the land. And this creates deserts on Earth. Have you ever noticed that all the deserts on Earth seem to occur at 30 degrees north latitude, like the Sonoran Desert in Tucson, where I used to live? Or at 30 degrees south latitude, we have the deserts of like the Nefu Desert or the deserts of Saudi Arabia and Africa. And Australia, to some degree, occur at 30 degrees south. These two interfaces create deserts at key locations on Earth as moisture is sucked out of the ground. So it's very interesting to think about the fact that our rotation is somehow causing deserts on Earth. That's not something you would actually think of as cause and effect until you go through the individual marble piece or the individual Jenga pieces, right? Now let's use our imaginations. Does anyone know what the rotation rate of Jupiter is? Let's look up the rotation rates of the planets. This was actually going to be one of the homework questions I had us work on about a week ago, but I kind of changed it last minute. Let's see if we could go to Google and let's see if we could do rotation rates of planets. And let's see if we can see that as a kind of chart. I'd like to see it in years as well as days. Oh, what the crap is this? Okay. Oh, it's all in days. Here. Don't look at revolution period. Look at rotation period, okay? What do you guys notice? Can you see any major differences? Let's just tackle terrestrial versus Jovian planets. Today, we want to begin our lecture learning about the Jovian planets. We want to talk about Jupiter, Saturn, Uranus, and Neptune. And up to now, we've mostly been talking about terrestrial planets, Mercury, Venus, Earth, and Mars. As I've made note of, Earth and Mars have basically the same rotation, one day, 24 hours. Mercury and Venus are quite a bit longer, so things are different for them. How would you compare the rotation rates of Earth and Mars to the rotation rates of all these Jovian planets? What's the big takeaway from this table here?
That even though that the Jovian planets are quite faster, they're still quite similar in terms compared to like Venus and Mercury.
Ryan, I think you had the first part of it more correct. See,
Okay.
Ryan, I'm also thinking about the fact that the Jovians are freaking humongous in comparison to Earth and Mars and Venus, right? Like their radii are 10 times as great,
Yeah.
meaning their volume is like thousands of times as great. It's remarkable to me, Ryan, that their periods are approximately half. They're all close to half a day. So you have a planet like Jupiter, which is a humongous planet, rotating in only 10 hours. To me, Ryan, that seems quite fast. What if we consider the Coriolis effect? What do you expect happen to circulation? If you could spin Earth up to twice as fast and make it rotate in 10 hours, what do you think would happen to the Hadley cells? Remember that on Earth and on Mars, a rotation of one day creates triple Hadley cells. Venus's much slower rotation gives it only one Hadley cell per hemisphere. So what would happen if you could speed Earth up to a rotation period of 10 hours?
Would you have more Hadley cells? They'd be broken down even more.
Yeah. And at that point, wait for it. At that point, your planet might look like this, wouldn't it? What's my message here? What's the point that I just made? I just want to make sure I didn't go over your heads here. I'm making a very simple point. I just want to make sure that you understand it.
I guess that if Earth rotated faster than it does, we would have harsh weather.
Oh, damn it. I did. No, my point was all the fucking stripes of Jupiter are Hadley cells, and that all the stripes of Jupiter are caused by the fact that it rotates so fast. That was all the point I was trying to make, right? Like, for instance, part of this class should be being able to answer simple questions like, why does Jupiter have stripes in its cloud tops? And you guys now know the answer, don't you? Explain it to me real simple, like a sentence or two. Why does Jupiter have stripes in its cloud tops?
Because the Hadley cells rotates the air to create the stripes.
Yeah, what causes the Hadley cells?
The fast rotation.
Because Jupiter has a fast rotation, it breaks circulation in the Jovian atmosphere into a set of multiple circulation cells. That must mean that what we're seeing here is quite complex, Jenna. There must be areas of rising air and cooling air, sinking air and rising air. Each of these must be a separate Hadley cell, just like the polar vortex or just like the Hadley tropical zones, right? In fact, I wouldn't be surprised if that had something to do with cloud condensation on Jupiter, right? Perhaps that would even explain some of those dramatic colors that we see. Let's leave the asteroid. Oh, jeez. Let's take a trip to the outer solar system. Let's explore Jovian planets. Okay, that little bit was to help understand. You know, the gas giants are basically all planetary atmosphere. The gas giants are also called the Jovian worlds or the Jovian planets. They consist of 4 planets that we will be discussing. Jupiter, which lies at a distance of 5 astronomical units from the sun. Saturn, which lies at a distance of 10 astronomical units from the sun. Uranus, which lies at a distance of 20 astronomical units from the sun. And Neptune. Neptune lies at roughly a distance of 30 AU from the sun. Notice the simple regular order to the distances from the planets, approximately so. People have often wondered about that. Oh, look at that little guy, Austin. What's that little dude?
This is Nachito Paquito. Omera.
Nachito Paquito is pretty damn cute, Austin. Look at that guy. He looks like he could fit in a teacup. Oh my gosh. Here, you can come look quick. Hold on. Look to the side. Look at Nachito Paquito. Girls are freaking out here.
Chihuahua I've ever seen.
Yeah, that's a tiny little chihuahua.
He likes to get.
I tried to show them Phil when you were in the shower, but Phil ran away. He was coming over here, but he's
Okay, Nachito.
Nachito Paquito. I wanted to be able to share an animal for the first time. Ever since my raccoon who lived in the sewer went away, I haven't had any animals to share with my students. And oh, here. So this is Phil. He's a big man coon cat. He's absolutely huge. He's like 25 pounds. There's all my students, Phil.
I actually have 2 Maine Coon cats also.
Really? Are they as big and fat as this guy here?
One's 26 pounds, one's 25 pounds.
You like him like the time, huh?
I love them.
This guy, he's all brand new to my apartment. We brought him back here this week, so he's getting the spot. Oh, look this Nachito Paquito.
He's a cat, and he's so fat that his name is Fat Cat.
Fat cat.
My bull's getting caught in his fur. Okay, I think I took off some tufts of fur. Anyways, fun to share Phil with you guys. Animals help the day go by. But Austin, is that dog new, or did you always have that guy?
Yeah, he's at Jenny's house. So whenever we're here, we have Nachito.
Okay. Damn, that's cool.
My cousin's house, who is my roommate, we have Penny.
Okay, that's right. That's right. Can they get along with each other? Or they probably don't see each other.
They've never met, but
Okay.
I would like to get them on a little date action, see what.
Okay. Back to the action here. Just so that you guys know, as we've been learning more about the gas giants, it's become sort of popular in modern day planetary science to kind of make a slight, even though these are all the gas giants and they have a lot of similar properties, we've started getting in the habit of thinking of Uranus and Neptune as slightly different. So it's become kind of voguish to refer to Uranus and Neptune as the ice giants. Let's go ahead and make note of that. These guys have a bit more ices than Jupiter and Saturn, and that's responsible for some of their appearance. For most purposes, despite their wildly different appearance, and let's go ahead and look at their wildly different appearances for a second. So here's the appearances of the 4 gas giants. We see Jupiter up top with its infamous stripy cloud tops, which I just related to Hadley cells. You'll notice that Saturn shows a bit of the stripiness that Jupiter has, although it's a bit more hazy and yellow, and I'll show you some pictures. It's much harder to see stripes in Uranus and barely able to in Neptune, despite their fast rotations. You'll notice that Uranus legendarily has a greenish color, whereas Neptune has a bluish color. Saturn has prominent rings, although all 4 Jovians have rings, which I can show you at some point. Despite their wildly different appearances, all of the gas giants have roughly the same composition. And the composition is very close to the sun. Let's write that down next. They also don't really have solid surfaces, although they do have solid chunks further down in their core. There's no kind of easy demarcation of where the surface of the planet begins. Okay. So for the most part, the composition is roughly hydrogen gas, usually in the form of diatomic molecules, 2 hydrogens stuck together. That makes up about 70% of the planet. Helium gas, usually in the form of monatomic helium. Helium doesn't form molecules, you'll remember, because it's an inert gas. Helium is roughly 28%. And then the remaining 2% could be broken down into what we would call, I'm going to refer to them as hydrogen ices. (1%). And then finally, a little bit of rock and metal somewhere in the inner core that might make up 1% of the planet. In fact, you'll notice that this is basically the composition of the sun, except in the sun we called these 2 things metals, but here we're really differentiating the difference between hydrogen ices and rock and metal. Hydrogen ices are something that we need to discuss for a little bit. Hydrogen ices are at the very heart of what makes the Jovian worlds tick, why they formed the way they do, and why they have such a variety of interesting geology associated with them. Okay, can I erase this? Let's start by taking an important concept down. Jovians formed outside what we would call in planetary science the frost line. The frost line is a concept that helps us to understand why terrestrial planets form close to the sun and Jovian planets form far away. Let's imagine we could take a trip back in time 4.6 billion years into the past to when the protosolar nebula was recently formed and our solar system was just a little baby. At the center of the solar system, you have the protostar, which will later become the sun. It's a recently smushed down ball of gas, and it's wicked hot, and it's giving off a ton of radiant energy. That light energy is traveling out into the disk of the solar system, such that the dusty gas near the star is quite hot. And just like in today's solar system, the farther out you get from the sun, the gas will be much cooler. The composition of the gas is basically the same composition as the Jovians: hydrogen and helium with 1% icy particles and 1% rocks and metals. Rocks and metals, as you know, are such that even at very high temperatures, they still remain in the solid phase. But ices, such as water, are called volatiles. Near the sun, where it's warm, ice would be in the form of a gas. Further out, where temperatures are cooler, ice would condense, the water would condense into something like ice. Remember that there is no such thing as a liquid in outer space, because you cannot have liquids without surface pressure or atmospheric pressure. So that means at some point, there should be this invisible line, this dotted boundary called the frost line, where water would go from a gas and deposit into an ice. And this idea is called the frost line. Let's look at a really crappy cartoon. And let's talk about how planets form so you can understand why this created the Jovians. Okay, let's imagine you were a planet forming interior to the frost line, a planet like Earth. You would be forming from whatever is solid in the protosolar nebula. Hydrogen is a gas, helium is a gas, and at this distance from the sun, water is also a gas. What is solid then are little flecks of silica rock like sand and little flecks of metal like chunky irons. These little tidbits form the seeds of planets. Now, the initial seeds of planets do not have much gravity associated with them. After all, if I take this lump of granite and I take this lump of iron, which could be comparable to the little bits of rock that were floating around the protosolar nebula, I cannot feel any gravitational attraction between them. It's just not there. What would happen is as they orbited the protostar, they would gently collide with each other. And at first, nothing more than static forces and just little bits of static cling would keep them loosely bound together. However, as more rock and dust began to accumulate on these chunky bits, they would begin to form something that we would call a planetesimal. And an asteroid is a pretty good example of a planetesimal. It's something that's nowhere even near the size of a moon, and yet does contain rock and metal and even sometimes ice. Let's look at a couple of pictures of famous asteroids. Unfortunately, I won't get to do a full lecture on asteroids, so we could talk about this. This is probably one of the most legendary asteroids because this one actually has a moon. It's known as Ida and Dactyl. Ida is a potato-shaped lump of rock, roughly the size of Rhode Island, and Dactyl, D-A-C-T-Y-L, is about a mile or two across and is maybe the size of West Warwick, okay, or smaller. And so this is kind of like having West Warwick in orbit around the state of Rhode Island. It's pretty weird. And some of these asteroids are actually just no more than loose piles of rubble or rock. The asteroid belt exists between the orbits of Mars and Jupiter. The asteroid belt extends from roughly 2 astronomical units just past Mars to roughly 3 astronomical units somewhere before the orbit of Jupiter. Let's see if we can get a picture here and magnify this. The asteroid belt is not a failed planet. If you could take all of the asteroids, so here's Jupiter at 5 AU, right? Jupiter's at 5 AU, Mars is at 1.5 AU, and the asteroid belt is somewhere in between them. If you took a giant cosmic bulldozer and you scooped up all of the asteroids and crushed them down into a singular object, it wouldn't even make an object the size of a small moon. In fact, all the asteroids combined together are roughly the size of a slightly bigger asteroid. The largest of the asteroids, which is more mass than all of the rest of them combined, is the famous king of the asteroids, Ceres. Ceres is actually so large compared to other asteroids that we've given it the designation of a dwarf planet, and it's roughly the same status as Pluto in our solar system. We did not even have a picture of this bad boy until 2015. So when I started teaching this class, I did not know what Ceres looked like. Now today I can show it to you. You can see it's slightly spherical in shape. It's covered with impact craters from the heavy bombardment. So that tells us not a lot of geology has happened there. Can you guys see those shiny patches? Those are ice on the surface of the rock. Kind of cool. If we could ever put a base on Ceres, we'd probably be able to mine water from it, which would actually be cool for the idea of creating a biosphere. You guys will remember I told you about that television show I like called The Expanse, which is a pretty cool TV show. A good part of The Expanse takes place, at least the first couple of seasons, takes place on a colony on Ceres. so you can see some of your favorite astronomical objects from this class in that television show. Why don't we see if we can do something intellectual? What if we could calculate the frost line? Okay, we have an equation that could do that for us. So how far from the sun is the frost line? We might be able to answer that question by using the legendary no greenhouse formula. Remind yourself that the no greenhouse formula tells you how hot a lump of rock or ice is based on its albedo and its distance from the sun. The formula is the temperature is 280 K, times the fourth root of 1 minus the albedo divided by the distance squared. What do you suppose the freezing point of water is in Kelvin?
Negative 273? No, 0. Wait, 273.
Okay, that's what it is on the surface of Earth, Austin.
273, right?
That's right. So 0 degrees Celsius.
The 0 is the coldest you can get.
Austin, if I took a lump of ice into outer space, would it freeze at a warmer temperature or at a colder temperature?
Well, there's no atmosphere, and there's probably no gravity.
Without
so
atmosphere, does that make things want to be solid, or does it want to make them be gas?
I don't know. I would say solid because something to do with temperature, but I'm not quite exact.
Let's reason.
I know, like
In
atoms,
science fiction movies, what do gases do when they are exposed to space?
they just are like gone.
They're gone. They try to separate. That suggests that in outer space, molecules want to be liberated from each other, correct?
It would suggest that it would try and be a gas.
Exactly.
So
This
then
tends-
the freezing point would be smaller, like colder.
In fact, when you do the research and you either calculate it or you take sample of stuff into the vacuum of space, in space, the freezing point of water is roughly, I only know it in Kelvin, it's 160 Kelvin. So what would that be in Celsius? Oh, I guess it would be,
113 Celsius.
wait, how do you do this again? It's a difference of 273 minus 160, right? Negative 113 Celsius. That's pretty darn cold, right? Things really want to be gases in the vacuum of space. What about the albedo? Do you guys remember what the albedo is? We have to consider the albedo of ice. What does albedo mean?
Is it how much sunlight is absorbed?
That's
Or-
right. Whether it's shiny and reflective or dark and absorptive. Would ice in space be shiny and reflective, or would it be dark and absorptive?
I'd guess dark, but the picture you showed us had shiny ice on the moon or on the
It
Ceres.
did look shiny on the surface of that planet, and I agree. But unfortunately, I've given you a garden path here. I think kicking around in the vacuum of space, based on the protosolar nebula, that the ice would actually be quite dirty. And here's one of my arguments. A few years ago, we actually created a spacecraft mission to land on our very first comet. Once again, I haven't gotten to talk to you guys too much about comets, but unlike planets, comets are mostly made of water ice with a tiny bit of dirt in it. And famously, the astronomer Fred Hoyle referred to a comet as a snowball with a rock in it, okay? If you ever did that when you were a mean little kid. In fact, typical comets are only seen because as they approach the sun, the ice surrounding that little tiny bit of rock will sublimate into a gas, and the gas reflects so much sunlight that you can actually see the comet with a bright tail in the sky. So that's all basically reflected water in outer space. Comets are usually made of more than 90% ice, but that little dirt goes a long way. Up until a few years ago, I could not show you a picture of the nucleus of a comet because that picture did not exist. To correct for this, we developed a spacecraft called the Rosetta Spacecraft that flew to a comet while it was in the outer part of the solar system, at least past the asteroid belt, and we attempted to land on it and take some photographs of it. Would you like to see a picture of what ice left over from the beginning of the solar system looks like? Of course you would. And I have them here. Here are some of these pictures of the Rosetta Comet. So here we are approaching it from several hundred kilometers away, and the spacecraft got closer and closer, and it even attempted to land a probe, a washing machine-sized probe, onto the surface of the comet. And I want to tell you about that. Now, the comet's rotating as we approach, so we keep seeing different parts of it. Notice from up here, the surface looks gray and almost something like pancake batter. The comet has an almost unpronounceable name to me. It was 67P Gerasimenko, and it was basically shaped like a rubber ducky. It had two lobes, and the lobes were rotating. One of the challenges of the mission was to get close enough to this rotating object and then to kind of start rotating with it so you could land something on it. Look at this stuff. Now, I'm telling you this is all ice, but what does it look like to you?
Dust.
It looks like rock or something black. One of the funny things about the lander that they tried to land onto this comet, because the comet has such a low mass in comparison to even, say, a moon, the escape velocity from this comet is so low that if you were to stand on it and jump, you'd probably jump into outer space in excess of escape velocity. So what they were worried about is obviously when the washing machine hits the thing, it's going to ding off it and bounce back off into space. So they designed it with these ice harpoons so that the ice harpoons would shoot out of the washing machine, lock into the ice, and kind of click it down to the surface. Famously, one of the harpoons must have had a tiny bit of water in it and it froze solid. So the harpoons didn't fire. And sure enough, this dumb thing bounced across the surface. And you watch the pictures of it, you can see it flying up into the quote unquote air, up into space. And there are all these pictures of the comet upside down and stuff. And finally, the thing landed on its side inside the shadow of a large ice boulder. It was annoying because they could see the thing lying on its side, taking a picture of the comet's surface, but they couldn't figure out which boulder it was in for a while because it was like there were all these different shadows it could have bounced to. So it compromised the science mission a bit, but we still learned some things. Look at all of that darkness. Ice in outer space is generally not clean because it's been floating around in the vacuum of space, not only bristling against the dust of the protosolar nebula, but then being subject to all the micrometeorites and gick that just floats around the solar system over time. In fact, the really close pictures of it, the surface appears quite dark. The average typical albedo of a comet is close to 3%, making this ice that is darker than the surface of the moon. As a point of comparison, you might consider this type of ice to be the sort of ice that you find in cities in the wintertime, dirty snow under tires. If you've ever been in the city after a snowstorm and you've seen that kind of really dirty black ice that accumulates inside cities, the book actually had a suggestion for a quote unquote science experiment. It was go out during a snowstorm and scrape some of that really yucky black snow off the back of your tire, under your tire, and take it home and put it in your mom's cooking pot and heat it up on the stove to melt away some of the water. And it asked the students to report on what they found left in the pan. Now, I was never crazy enough to do this because I didn't want to put dirty snow into my pasta pot. But I suspect the point is what would actually be left over once you boiled away the water would actually be a very small amount of sand and grit. It doesn't take a lot of dirt to change ice's albedo to black. So although it did look shiny at the surface of Ceres, the typical albedo of a comet might be 3% or 5%. All right, now we can go about calculating the frost line. The frost line will be a distance based on the darkness of the snow, 3%, which we're going to call dirty snow, and the temperature, which will be in space 160 Kelvin. 160 Kelvin equals 280 Kelvin times the fourth root of 1 minus 3% over the distance squared. Let's see if we can reduce this a little bit. Let's divide 280 by 160 and apply the fourth power to both sides. 160 over 280 raised to the fourth power. You guys know what 1 minus 3% is, right? What's 1 minus 3%?
9.97.
0.97, 97%. Now, we're going to flip the d squared up and the 160 over 280 down, and I'm also going to square root to get rid of the d squared. What we will end up getting is this. The distance is the square root of 97%, over 160 over 280 to the fourth power. Let's see if we can do this together on our calculators. 97% divided by, open parentheses, 160 divided by 280, close parentheses. That's just the close parenthesis part. So let's raise that to the fourth power. Shift 4 equals. That equals gives us all of this. Now we'll take the square root. Shift square root. Wow. How about that? Is that a cool frickin' answer or what? The answer is 3.0. And what are my units again for distance in this formula?
AU.
Jenna, do you see why I find that to be such an amazingly neat and tidy number? What does that mean to me, Jenna? Why would 3.0 be like a perfect? Of course.
Oh,
Yes. Yes.
well, is it something about the distance?
Something about the distance.
Because Jupiter is 5 AU, we're 1, so that's 3. I don't know.
Something like that. Now you're getting colder. You're getting warmer. Sorry. You're getting warmer. You're right at the frost line. What do we have at 3.0 astronomical units? I'm trying to give you a hint with what I had on the screen there.
The asteroid belt.
That's the edge of the asteroid belt. What a very neat and tidy answer we found, huh? This is the edge of the asteroid belt. All right, Jenna, I'm going to push it even farther. What's my point? Explain the picture that I'm trying to present to you.
The point is that the asteroid belt is the distance from the sun that creates the frost line.
Right. So in other words, I'm talking about terrestrial formation versus Jovian formation, right? Imagine, Jenna, that I was forming a planet outside the frost line. Maybe I didn't complete the concept for you. Maybe it's my fault. In the inner solar system, when you form a planet, the only materials that are solid are rock and metal, and the rocks and metals go into forming these asteroid-like objects, which through collisions and eventually through gravity will condense into a planet. Composition of Earth, Venus, Mercury, Mars, rock and metal. Now imagine you were forming a planet outside the frost line. Instead of being only able to form a clump out of rock and metal, you'd now have frozen ices adding to your Jovian Planetesimal. And roughly, what is the ratio? I took it off the board, but if you look at the composition of Jovians or the composition of the protosolar nebula, what is the ratio of ice to rocks and metals in the protosolar nebula?
They're equal.
No. Ice is equal to rock and metal combined, Jenna.
Okay. Yep.
In other words, there's twice as much ice as there is rock, and there's twice as much ice as there is metal. As a result, Jenna, you can form much larger planetesimals. You can form much larger seeds that begin to form planets. Okay, walk me through it, Jenna. Why would a larger planetesimal allow me to form a Jovian planet? There's one last puzzle piece in the chain of reasoning. So what, a student says. So you got a bigger planetesimal. Why does that mean I turn into Jupiter? What did you learn about in, say, your atmospheres class that would help explain why the larger planetesimal could end up forming a Jovian? Let's start here. Why did Earth not capture? Let's look at a picture of a planet forming. Here's a cartoon picture of a planet forming within the protosolar nebula. This is what it would have looked like as either Earth or Jupiter formed. Remember that most of this gas is hydrogen and helium. Why didn't Earth capture any of that hydrogen helium into its atmosphere or planetary body?
Because Earth wasn't big enough. It didn't have the gravitational pull to actually
Hold on
contain
to those
hydrogen.
gases. Good idea, Ryan. In fact, in the language of chapter 10, our last week's lecture, those gases would have had a high thermal escape speed, and they would have been able to just bounce right off the planet's gravity, right?
Yes.
Okay, Ryan, so then if you understand that, why would forming a Jovian out of rock and ice change that? I'm not looking for any complex answers here. Very simple ideas.
The ice.
What about the ice, Kim?
The terrestrial planets don't have ice when they're formed.
And how does the ice lead to the capture of hydrogen and helium?
Because it's frozen.
Yep. You a hint. I want the student.
Well, oh, gravity,
Mass.
the mass. I'm sorry.
You're adding mass. Yes, Kim, gravity, but you're just missing a very simple word, mass. If you add ice to your terrestrial, you are increasing the mass and thus the gravity, and eventually you increase the amount, you get so much gravity building so fast that you can actually begin to capture hydrogen and helium from the protosolar nebula. The next thing you know, instead of having a planet that looks like Earth or Venus, you end up with a planet that looks like this. All of the gas that you see is captured protosolar nebula hydrogen and helium, just like the sun's hydrogen and helium. However, do you see all these beautiful colors? These beautiful colors have nothing to do with hydrogen and helium. Let's take notes on that.
Do they have to do with neon?
Well, neon doesn't have a very high abundance in the protosolar nebula. They have to do with the hydrogen ices themselves. Up to now, I mentioned hydrogen ice and water, but you guys need a little chemistry lesson on what types of things could freeze out of the protosolar nebula. Neon is not a very popular gas out there. There are molecules that have a much greater abundance than neon.
Argon?
Sorry?
Argon?
Even argon would have a very low abundance. Now, oh, by the way, I need to make a pitch here. Anyone who would like to take another 4-credit lab science, please sign up for my Astronomy 1020 class in summer 1. The selfish reason being that I would also like to offer Astronomy 1020 in summer session 2, because I think it should always be available for students to take. Right now, they have not opened up an Astronomy 1020 session in summer 2 because they doubled my caps to my class. And so I think my 1020 class in summer 1 is like half full. I want more people to take 1020 in summer 1 so that they'll open up even another section. That way students who have fun in my 1010 class summer 1 could then take it summer 2. What are the benefits of taking it? You already know my teaching style and you know that I'm going to help you out. Same formats. We do the homework the same way and all that stuff. The initial part of the class is the same and it splits off, so you'll already know what's going on. And plus you get more time to hang out with me. What could be better than that? These classes also transfer to all universities in Rhode Island or wherever else you want to go. You did sign up for it, Ryan. That's great. I also like having some veterans around because they, oh, hey there, Kim, you got a little kitty. Is that a dog? I can't see. It's so dark there. Oh, that's a little pooch.
Yeah, Luna.
Luna, that's right. Yeah, we want to see more of Luna, Kim. So thanks, Ryan, for signing up. But don't take it unless you need it, of course. But if you do need another lab science class, you'll have a great time with Astronomy 1020. We'll actually leave the solar system and talk about stars and galaxies.
Professor, isn't it free too? I think they made all summer classes free, unless I'm wrong.
I think you have to have a certain GPA.
Really? If you have a certain GPA and summer classes are free, why the hell wouldn't you do it? Hey there.
Anyone can take it, but
They-
she's a little nervous because she learns a little slow, Professor.
Jenny, you don't have to be nervous. All you have to do is just show up and copy what I copy down. There is a test, maybe one, but if you just show up, you can't really fail the
I
course.
always do this
You just
stuff.
have to hang out. And hell, you're already hanging out. You should get credit just for being there and listening. Okay. So please take it. Take 1020 in particular. Okay. Enough of my proselytizing. Let's talk about hydrogen ices. They're important because they determine the colors of the planets. Sometimes planetary scientists call them hydrogen ices. Another name for these things are called volatiles. Do you guys know what that word means?
Unstable.
Unstable is one way to look at it, but in a chemistry sense, it means unstable in that it easily wants to liberate itself from a solid into a gas, or it wants to evaporate easy, right? For instance, carbon dioxide is considered a volatile because it wants to, and the reason that that the term unstable, Kim, is associated with volatile, because we think of things turning into gas as increasing entropy and increasing chaos and disorder. So that literally leads itself to a volatile person is someone who's unstable and are going to quickly turn themselves into a bunch of molecules. Okay, something like that, right? But volatiles means it wants to either evaporate or in space, it really wants to sublimate. Another way to think about volatiles is low melting points or low sublimation points. Probably one of our most iconic volatiles would be ice or water. Water, whose chemical structure is an oxygen with 2 hydrogens, tends to form white clouds when we see it in the atmosphere of Earth. And in fact, the white clouds that we're going to see in the atmosphere of Jupiter are also made of water, just like on Earth. There are other substances that quickly condense. Carbon dioxide is considered a volatile because it quickly goes from ice to gas at low temperatures, even like Earth-based temperatures. But CO2 is technically not a hydrogen ice. What hydrogen ices have in common is they have a popular atom like oxygen or nitrogen or carbon, and they have hydrogen stuck to them. Another one that you might have heard before is called ammonia, which is a nitrogen with 1, 2, 3 hydrogens stuck to it in a kind of tetrahedron-like shape. So the chemical symbol for ammonia is NH3. Water is H2O. When ammonia condenses into a gas, it tends to form some yellow clouds. I'm going to make mention of a more elaborate hydrogen ice. I've been trying to show you guys simple ones, but there's a particular cloud band structure on Jupiter that makes very red clouds. So let's take a quick look at the cloud tops of Jupiter. Notice that you guys can see some white clouds. You guessed it, that's just condensed water, just like the white clouds on Earth. You can also see some yellowish clouds, and those are, of course, due to condensed ammonia. Let's talk about what makes those brownish red clouds. That's a particular hydrogen ice called ammonium hydrosulfide. Ammonium hydrosulfide does not appear too much on Earth unless you're one of those Mad Magazine pranksters that likes to play with stink bombs. Stink bombs are these silly kids' toys that make a stinky fart smell when you break open the glass. I don't know if they're that popular these days, but when I was a kid, they'd be around. Or maybe I was just the kind of kid that would throw a stink bomb. Maybe that's who I was. The stink bomb is made of ammonium hydrosulfide, and it's got a kind of strange chemical structure here. It's nitrogen with 4 hydrogens stuck to it, and then a sulfur and a hydrogen. It's that sulfur which gives the stink bomb its stinky, stinky smell. Here we go. NH4SH. I can never remember how it. It's a solution, not a solid, but it's a substantial component of the cloud decks of the gas giants, both Jupiter and Saturn. NH4SH. The ammonium hydrosulfide is responsible for the red clouds. So normally that wouldn't be something this is something you learn about in your chemistry class, but it's important in planetary science. Lastly, we have the compound methane. And methane's symbol is CH4. It's kind of, it's like the propane you use in your gas grill. It's a carbon with 4 hydrogens. And it's responsible for blue clouds. Famously, methane, once condensed into clouds, makes blue clouds. Now, these do not all have the same freezing point of water, which is 160 Kelvin in space. But what makes hydrogen ices volatiles is the fact that they all have a kind of similar temperature at which they will condense into clouds. They're lower temperatures. Let's compare that to, say, granite rock. If you wanted to melt this lump of granite, you could do it, but you would need a furnace that could raise your temperatures up to close to 2000 Kelvin. So compare the melting point of rock or metal, which is 2,000 to 3,000 kelvins. And by the way, that's 2,000 to 3,000 Kelvin is much hotter than the temperature of a fireplace. So, you know, we could, just from life experience, we could throw these lumps of rock and metal into a fireplace and they would not melt. Their temperatures to melt are very high. Ices like this, they all melt at like 160 Kelvin, which is easily the kind of temperature you could find in space. Okay. We know some things about the cloud tops of Jupiter thanks to a spacecraft mission called the Galileo spacecraft. And let's take a moment here. How am I doing on time? Oh God, I'm doing bad on time. Okay, I got a better idea. Let's summarize what we've learned today by taking a big think about how these hydrogen ices affect the moons and the planets of Jupiter. So you've learned a lot of building blocks today, and next time I'll unleash them all on you. Can I erase this, folks? All right. Outside the frost line, new types of geology emerge. For instance, you guys know that the dominant form of geology on the moon and the dominant form of geology on Mercury are what?
Impact
Cratering.
Impacts cratering. And why are the surfaces of those two moons dominated by impacts cratering? This is a question I'd expect you guys to know the answer to.
This is no other active form of geology.
And
They're-
why isn't there another form of active geology on those
Because
planets?
they're for, say, volcanism and plate tectonics rely heavily on thin lithospheres,
And then
which
look at,
is a frozen layer. And over time, the frozen layer will keep sinking deeper and deeper to the core.
so why is the lithosphere thin on Earth but not on the moon?
because the moon doesn't have a core.
The moon does have a core, but not a big one. All right,
No,
then
Adam.
it's not about atmosphere. No. What? How about Mercury? Mercury has a core. Why doesn't Mercury have a thin lithosphere?
It's because it has it's a small radius. The
That's
bigger the
right.
planet, the
Now
longer
you're
the
understanding.
lithosphere will stay thin.
It's about planetary size. Small size, cold core, thick lithosphere, no geology, craters. Now, Ryan, obviously we're not going to be able to have geology on the gas giants themselves, right? Because they're just atmosphere. And as you sink down into them, it just gets thicker and goopier. But the Jovian planets all have dozens and dozens of moons. Jupiter has like 60 something moons. Saturn has 60 something moons. If I were to show you a quick sneak peek of what you will learn in our last lecture, not only will I talk about the atmospheres of the planets, but I'd also like to talk a little bit about their moons. And let me try to give you a hint of where I'm going with this. I'll show you this next time, but I want to summarize today's class with a point. Function F559. Knowing Ryan, because you were with me here on the planetary size thing, in comparison to Mercury and the moon, several of the moons in the outer solar system are actually larger than the planet Mercury, and many of them are even larger than our moon, but they're comparable to the size of a terrestrial planet. Ryan, knowing that these big moons are roughly the size of Mercury or the moon, what would you expect the dominant type of geology to exist on these moons to be?
I would say impact cratering. I'm
And
not sure if they have atmospheres, which
might affect things. It
Yeah.
turns out that, Ryan, even though they're small, and even though small things don't have active geology, the whole game is changed outside the frost line. Inside the frost line, the lithosphere is made of rock, which is hard to break. But what do you think the lithospheres are going to be made of outside the frost line?
Probably ice.
And ice is easier to melt because it's a volatile and easier to break. And that means we're going to see tons of wacky, cool geology, a bizarro inverted type of planetary geology based on ice. What can you expect next class? Have you ever heard of cryo volcanoes? That's volcanoes that spew geysers of methane and water ice up into the atmospheres of their planets. Cryovolcanoes are cool. They might even freeze out and turn into crystal forests that you could walk through. We're also going to see ice tectonics, where sheets of ice crack under the fractures and stresses of their planets. There's even frost jet erosion. And you guys saw some examples of that in last week's lecture, when gases sublimate and blast across the surface of the planet. And then lastly, we're also going to see ice craters. In fact, do you remember earlier how Austin was bamboozled by the fact that the ice was shiny on the moon Ceres? Do you want to know why that ice is so shiny, Austin? The ice is shiny. Yep. Why is the ice shiny on Ceres? It's shiny because that's probably where impact cratering blasted the dirty ice that's on the surface and released some of the fresh, shiny ice underneath the dirt. And you're going to see that in particular on the moon Callisto around Jupiter. Next week's class will actually, our last class is actually going to be really cool because I'm going to show you guys awesome pictures of all these Jovian moons. What do you notice about the impact craters on Callisto? They're all shiny because as the meteoroids strike the surfaces of these planets, they kick up fresh ice hiding under the grit and dirt. And the craters therefore look shiny in comparison. Anyways, you get my point. Ices change geology in the outer solar system and make it weird. And that makes this stuff kind of fun. The moons are actually geologically interesting. Okay, next class, we delve into the interiors of Jovians to see what's underneath the hood, and then we talk moons and we'll do a homework. Class, we're about to do a lab, and the lab that we're going to do today is called the rotation of Jupiter. It involves a little simulation, the CLIA exercises, which I have on my laptop. We're basically going to look at an image of Jupiter. We're going to follow the rotations of the moons, and then we're going to use Newton's version of Kepler's third law to calculate the mass. Let's talk about what you're going to need to do this. To do this, you are going to need today's data sheet, okay? And you're going to need to print out at least 2 pages. Let's go to lab. Sorry. Lab 11, the rotation of Jupiter, okay? Let's look at the PDF. You only need a couple of pages from this PDF. It's pretty extensive. There's some data that you need in here, which I will walk you through. But what I'm going to do today is first I'm going to record so what we're going to have is a simulation where you can see Jupiter and you can watch their moons kind of orbit back and forth in front and behind Jupiter. And we're going to measure the position of the planet. We're going to record the date, the time, the distance to the moon in Jupiter diameters. And then we're going to use this with Newton's version of Kepler's third law to calculate the mass. Here's what pages I want you guys to have or to recreate. I need you to have table 1, where we're going to record the data. Okay? So that's page 5 of the lab. I also need you to have the plot for the moon Io, which is page 7 of the lab. I also need you to have one more page, which is the analysis section, number 15. So if you're printing from your home computer, or if you're reproducing this in a table on your notebooks, I need a minimum of, I just need these 3 pages, page 5, page 7, and page 15. Okay, that's the first issue. The second issue is, before everyone started showing up to the live session, I was debating whether I should do the lab with you live or have you watch the pre-recorded lab, which is, yeah, Austin?
5, 7, 15.
5, 7, 15, those 3 pages.
Okay, sorry.
All right. I also came back from New York last night quite late, so I didn't finish my grading, and I'm definitely concerned about that this semester. There's also a number of students who want like little progress reports so they can know how they're doing, and I would like to get all of that in. So to help me catch up to this work that I'm a little behind on, it would be kind of nice if, since there's only 4 of you, if I could farm out the lab to one of the, I actually have a nice pre-recorded version of that. Is that something you guys could tolerate for a day so that I could use this next hour to help catch up to your grades and give you guys the progress reports you need? Would that be fair? All
Yeah,
right.
I'm fine with that.
And
Everyone
it wouldn't
else is.
offend anyone, right? It wouldn't. All right. That would be so lovely for me. So here's what I'm going to do. I'm going to stop the recording now so I can start to process the video for today's lecture. And then if you guys can just sit with me for a second, there's probably 2 different versions. I have a question at the end of class. That's fine. Is it a question that everyone in the other, is it beneficial to have it on the recording, Austin?
Unless someone cares about my grade on the recording, I don't think so.
Okay, then I'll wait until we're stopped the recording. So see how Austin has a question about grades? I'm getting a lot of emails like that, and I didn't get to it last night, so I could really use an extra hour in my day today. Okay, so I'm going to stop the recording, and then I will post the link to today's lab in the announcements right under. It'll show a link to today's lecture, a link to today's lab. You've seen me do this before, but if you guys wouldn't mind hanging out for a second, we can find the best link, and I'll give it to you right now so you can get started after your own personal tea break. Sound like a plan? Okay.